to start off with a bit of review. And one thing I want to make sure you guys really know the difference between is flow control versus congestion control. So can someone tell me what flow control is? So flow control is to regulate the sending rate to match the receiving rate. All right. So the analogy that I gave when I introduced this is if we have a bucket here, and the bucket has a drain in the bottom that drains away the water that's in it. Then we have some sort of faucet dripping water into this bucket. Flow control regulates the rate at which this source sends, it puts water into this bucket so that we never overflow the bucket. And also we don't want to underflow the bucket, meaning we don't want it to ever run out, right? As long as we have more water to send. So the difference is congestion control controls the entry of traffic into the network to prevent congestion collapse, all right? So we control the entry of traffic into the network to prevent congestion collapse. All right, so if you recall from last time, I learned about TCP's congestion avoidance mode. And there, TCP is increasing its window size linearly, and it's attempting to avoid congestion. It's attempting to regulate its flow, so it wants to maximize the amount of data that it's sending to the destination, while at the same time preventing this congestion collapse in the network. So we can sort of extend this analogy for congestion collapse, whereas if we have this bucket, we again have a drain at the bottom going to our destination. Then congestion control, now we have multiple faucets putting water into this bucket. All right. And we somehow want to be able to prevent this bucket from overflowing, which is congestion collapse. But these sources are all distributed and they do not communicate with each other, all right? So they don't coordinate and say, okay, you go at this rate and I'll go at this rate. They have no communication with each other, and instead they work in this distributed fashion. And because we have congestion control in the transport layer, then they can never, they will, in TCP at least, they will overflow this bucket because that's how you know that there's loss. But they don't get complete congestion breakdown where they're all just trying to pump packets or drops of water into this bucket out. And so it's continuously overflowing. All right, so this is the difference. So this is a key concept to know, all right? Then let's just review some of the other things we learned last time. So we learned what a timeout was. So can someone tell me what a timeout is? The time until we declare a packet lost. All right, so visually we can indicate this using our time diagrams here where we have the source sending to the destination. So visually we can represent this as the source sends a packet to the destination, and the destination sends back an acknowledgement. And here, if this duration is past our timeout value, then we declare the packet lost, all right? So then if it sends another packet and the acknowledgement comes too late, it comes after the next timeout, then we would have thought that this packet did not reach the destination because we did not receive the acknowledgement in time, all right? So everyone has that. Then the other way we can detect loss is with the triple duplicate ACK. And so visually, I'll just represent this visually. What we have in this situation is we have a window size that's, at least 4 packets large, and we send, we'll assume that this second packet was lost. So we're sending a bunch of packets. We receive acknowledgements for them. And we see that these acknowledgements came out of order. This was packet 1, 2, 3, 4, 5. So we got the acknowledgement for packet 1, then the acknowledgement for packet 3, 4, and 5. So here, this is the triple duplicate ACK, all right? Because we received the 3 acknowledgements, the acknowledgements for packet 3, 4, and 5 before we received the acknowledgement for packet 2, all right? So does anyone know why TCP handles these loss events differently? So the answer is that the timeout is a much worse form of loss than a triple duplicate ACK. And the reason why is because here, if the amount of time it takes to timeout, that means we're not getting much through the network. Whereas if we get the triple duplicate ACK, at least some packets made it through. At least 3 packets after the one that was lost made it through. So we don't need, there's not as much congestion in the network, so we don't need to cut our sending window back as much. All right? Now I just want to emphasize that there are many different versions of TCP. So the version of TCP that I went over last time is called TCP Tahoe. There's been extensions onto this. We're not going to go over those. So the version of TCP that your computer uses today is slightly different than the one I talked about, but the concepts are the same. All right? And then the throughput that TCP achieves is different than the window size. So the throughput is equal to our window size divided by the round trip time. All right, so it's important to distinguish between the actual throughput achieved and the window size that you're using. All right, so the window size is the number of unacknowledged packets you can have, and it's related to the throughput, but your throughput does depend on the round trip time. All right. So last time we ended with some analysis of TCP, and so we're going to continue that, and we're going to go over the drawbacks of TCP now. All right, so there's several, and we're going to go into a bunch of these. So the first one is that we discussed last time how TCP provides fairness. But this fairness can be gamed. So what do I mean by gamed? I mean that a malicious user can get more than their fair share of the bandwidth if they want to. So the way they do this is you open a bunch of connections at once. So let's look at an example here where we have host A, we have host B, and they are sending through some bottleneck link, like this, to, let's say, different destinations. So we have destination, and let's call it the C, and then destination is host D. All right? So if they both open one TCP flow, we know that as long as they have the same round trip time, they'll get an equal share of this bandwidth. All right? But what happens now if A opens up multiple TCP connections? So here, A has 4 TCP connections and B has 1. Does anyone have an idea what would happen here? A can get 4/5 of the bandwidth and B gets 1/5. So this malicious user A turned out to get way more than half the bandwidth, all right? And by creating more and more flows, it can get an increasing amount of the bandwidth up to pushing it up as high as it wants. All right, so this is a well-known problem with TCP. There has been some work to alleviate this problem, but it still exists in the internet today. And in fact, the way that web browsers work is they do open multiple concurrent TCP connections like this to maximize their throughput. So they're not acting maliciously, but they are acting in a way to maximize their own good. But because everyone does it, then it sort of evens out, all right? Okay, so let's look at another drawback. So the second drawback is that TCP assumes that a packet loss means congestion. All right, but this isn't necessarily true. So for your homework assignment, I asked you to think about this type of scenario when you have a wireless link. And wireless links tend to have pretty high loss rates because of things like interference and so on. And so if you're using TCP, it thinks that any of these packet losses are because of congestion in the network. When it turns out it could just be because that your wireless signal collided with somebody else's wireless signal, and so it's really, there's no congestion, it's just that you sent at exactly the same time, so there was this collision. And it gets really bad when we have high-speed links. So as an example, in a data center network, these servers have very, very fast connections to the network. So they typically have a 10 gigabit per second link. Okay? So to put this into perspective, your typical home internet connection might have something like 10 megabyte or megabits, which we'll just say is approximately, just for convenience, one. Actually, sorry, I don't need to convert. I was going to convert to megabytes, but we don't need to. So your home link has 10 megabits. And if we convert this to megabits, we have 10,000 megabits per second. All right, so this means that the average data center server has about 1,000 times more bandwidth than your home computer. All right. And so, because of this very high rate, any packet loss causes you to drop your windows significantly, right? So let's assume we have this 10 gigabit per second link, and let's assume that each packet holds 1,500 bytes. All right. So in order to maintain a 10 gigabit sending rate, our window size needs to be huge. It actually needs to be, W needs to be equal to 83,333. All right. So we need a very, very large window size. Now, because of the way TCP works, whenever we have a packet loss, we cut our window size in half. This means that in order to maintain this large of a window size, we can only have one packet loss every 5 billion packets. All right. So even with a wired connection, like an Ethernet connection, it's very, very, very hard to achieve this low of a loss rate. Because, you know, when you're sending bits across the wire, things get flipped. There's sometimes interference on the wire and so on. And so because of that, this loss rate is actually not really sustainable. And so we have to do other things in order to make TCP think that its packets weren't lost. All right? So we'll go into that in a little more detail in a minute, but let me continue on looking at these weaknesses. All right, so one more is that it detects overload using loss, or detects congestion. Right, so this means that in order to find the actual bandwidth of the link, TCP has to cause packets to be dropped. All right, so this means that TCP has to fill up the buffer at the bottleneck. All right. And so this means that the buffer at the bottleneck will always be nearly full. It'll either be full or at least very close to being full. So then if you have a burst of traffic, then most of that burst will be lost. So an example of this, again, if we go back to look at data centers. So in data centers, a common workload is one server will ask hundreds or thousands of other servers to do a bunch of work for it and will reply with their answers. So this is exactly how Google search works, for instance. So you have an incoming request, like it could be a search query. And this master server partitions the request to many, many other servers. All right, so typically for a large-scale service like a Google search, this is on the order of about 1,000 servers. All right, so it asks these 1,000 servers to do some computation, and then they reply with the answer. So if you're searching for something, they'll run the search at each of these individual 1,000 servers, and then reply to the master with, okay, here's the results. The master aggregates all the results and replies to you, to the user. Well, it turns out that all these servers do about the same amount of work, so they all reply at once. All right? And so this creates a large burst of traffic, and because TCP has kept the buffers full, then it creates lots of losses. So many, many of these replies are lost, and then by doing so, the master either has to ask them again for the reply, or has to wait for TCP to time out, which can take, so the default value is, about 3 seconds on today's internet. So data center operators tend to set that much lower, but still, it's you have to wait a very long time, so that can delay your search query and so on. All right, so this problem is called incast. All right, because we have many servers replying at the same time, and it creates this burst of traffic, creates lots of losses. I'll go over your homework questions with you from the previous times. All right, so one question that probably 95% of you got wrong is it possible for an application to have reliable transport over UDP? All right, so can we have reliable transport All right, so now I marked this very leniently. If you said, okay, UDP is not a reliable protocol, I gave you half a mark. But to get the full mark, you have to say, yes, we can actually do it. And the way you do it is the application itself has to do the error checking or provide the reliability. So the app has to, let me actually say implement the error detection. So now, can someone tell me how an application could do this? Yes, you could. There is a protocol that you could do this with. But, I mean, so why can't the application itself do the acknowledgements, for instance? So you send the data with UDP, and both applications know that they need to acknowledge each other, right? You can actually implement TCP right on top of UDP, all right? There's no problem with that. You can build on top of other protocols. So the applications themselves need to ask for the acknowledgements and do the timeouts and do these. You could do triple duplicate acts and so on, all right? So the applications can implement any of this stuff, but the reason we do it in the transport protocol, or in the transport layer, typically is to make it more convenient. So that when you're writing an application, you don't have to handle all this yourself. It's already, somebody else has already written this code, and you just use what you just build on top of what they've already implemented. So one other homework problem. So most people got this. So what network characteristics affect the performance of a stop and wait transport protocol? So stop and wait protocols, what matters is the round trip time, all right? So if you recall, we have this protocol where you send a packet and you wait for an acknowledgement to send another one. Right? So if we use this throughput equation that we learned last time, the throughput of this is 1 divided by the round trip time. Right? So that means the smaller the round trip time, the larger this throughput is, and if we have a large round trip time, then we have very low throughput. And you can see that with this type of diagram, because if we had a low round trip time, we have something like this, where we're sending lots of packets in nearly, we're using more of the channel, more of the bandwidth, whereas if we have a long round trip time, we're having lots of waiting time, all right? The question asks you, if you have two senders, you have sender A, sender B, they're sending across the bottleneck link, and they have different round trip times. This sender has 10 millisecond RTT, and this sender has 100 millisecond RTT. All right? So in this case, do they get a fair share of the bandwidth? It does not provide fairness in this situation, and that's because TCP depends on the round trip time. I mean, you can look at it just using this same throughput equation, that this guy will get whatever, if we assume that they have the same window size, then this guy will get 1 divided by 0.10, 0.010. This will be its throughput, and sender B gets 1 divided by, W divided by 0.1. All right, so that does not provide fairness in this case. The thing that will happen is their window sizes will stabilize to the same window size, but because the throughput depends on the round trip time, this host A will get more of the bandwidth. So let's switch back to our TCP analysis. All right, so we've gone over a couple drawbacks. Another drawback of TCP is that it's sensitive to our settings. So it's sensitive to the threshold. So if you recall, we had this threshold where after TCP starts in slow start, and after it hits this threshold, then it goes to congestion avoidance mode. So this setting of the threshold affects the performance of TCP, right? Because if we have this threshold too high, then TCP will overflow the network right away and will cause congestion initially, right? However, if it's too low, if it's down here, then what will happen is the TCP sender will just ramp up just a little bit, and then will take a very long time to potentially reach the full utilization of the channel, all right? So we need to sort of figure out how to set this threshold. You can use empirical measurements and so on, but really today it's just set with a heuristic that says, oh, this usually works, all right? Then another thing it's sensitive to is our initial window size. So our initial window size is set to 1, typically for TCP. And so this means that we have to do this slow start phase where we start out very slow. We start out really low down here, right? And this might have been appropriate 20 or 30 years ago when links were very slow, but today, there's quite a bit of bandwidth available on the internet. And so I asked you this in your homework questions. So some Googlers have proposed increasing this initial window size to 10 rather than 1. And so the advantage of that is that when you're requesting web pages are typically pretty small. They're on the order of, say, 15 to 20 kilobytes. And so if your window size is 10, then you can actually get the entire web page within your initial window. All right. So with this window 1, it takes about 3 round trip times to get a web page. And so this means that you're paying this penalty of 3 times whatever your round trip time is, whereas if we set it to 10, then we only need 1 round trip time. One final drawback of TCP is we talked about this 3-way handshake. All right, so in the 3-way handshake, the source sends a SYN request, which says, hi, I'd like to open a connection. This is my initial sequence number. And the destination replies with a SYN ACK. And the source then finishes this off with a SYN ACK ACK. All right. So one attack that you can do is you don't finish this handshake. So the source sends the SYN request. Then the destination replies with the SYN ACK. And then nothing. You just wait. The source just waits. All right? So what happens here is the server has to hold this port open. Right? It has to hold this connection open. And so by doing so, if you launch a bunch of these SYN requests, then you can take up all the resources at the server. All right? So this is called SYN flooding. And this is a form of denial of service attack. All right, because, and by the way, this is typically abbreviated DOS. All right, so the goal in a denial of service attack is to use up as many of the resources of the server as possible so they can't serve legitimate users. All right, so you can think of, we have Amazon here, and say you're a hacker group like Anonymous, and you want to bring Amazon down. One way to do that is you open a lot of SYN connections to Amazon's web servers. Then they're sitting around holding these connections open, wasting resources that they could be using for legitimate customers, right? And this has been done in the past to bring down some pretty large websites. Now it's much harder today because of like massive data centers and cloud computing, because Amazon has hundreds of thousands of servers, so they can just start up more web servers if need be, but it still is expensive for them. So typically outages today aren't so much, maybe 10 years ago they were because of denial of service attacks. Today they're typically because of user error. Like someone misconfigures something. That's generally today. Okay, so can someone tell me why TCP has these drawbacks? Well, you had a question first? So the question is basically, can the users manipulate the headers? And yes, you can. All right. You can do that. There are ways, for instance, to fake your IP address and so on. And we'll get into this stuff later. We'll talk about security near the end of the class, of course. So why for instance, does it assume that packet loss means congestion and that it has to detect overloads using loss? So it has this because the only information it knows is packet loss. All right? So the only info TCP has and because of this means that we have to overflow the buffers in order to find out how much bandwidth there is, to find the amount of available bandwidth. All right, so if we go back to last week, a week ago, we talked about different methods of flow control. And one thing we talked about was explicit congestion notification. All right, and explicit congestion notification gives us much more information about the state of our network. Because the way this works is that when a buffer is nearly full, we mark a field in the packet, so we mark the congestion field. All right, and by marking this, we've given the sender a little bit more information about the state of the network. We told them, hey, we're approaching capacity, so you should back off. All right? So instead of having to go past the capacity of the network in order to find out when to back off, we can do it sooner. All right? So this is explicit flow control because we're giving explicit information to the senders. So this has the advantage that we get away with this overloading buffers, we get away with all these losses and so on. But it has a serious drawback of requiring that all devices in the network support this. Right? The question is like, are you forced to obey this? And so, I mean, basically for this discussion, except for this, we're sort of assuming that the senders behave, in a well-behaved manner, that they're not trying to get more than their fair share of bandwidth and so on. Okay. Yeah, I mean, you could ignore it, but you also could use UDP instead of TCP and get more than your fair share of bandwidth. Okay. Okay, so but the serious drawback of this is that all network devices have to support it. So this means that if we're sitting here, we're researchers, we come up with the greatest explicit congestion notification protocol ever, and we prototype it and we implement it in our lab, and we're like, wow, this thing is great. There's no way it will actually get implemented in practice, right? Because in order to implement it, you would have to change every single switch and router on the internet, and that is not going to happen. All right, that would cost billions of dollars and just wouldn't happen. So that's the big advantage of implicit notification, is that in order to change the protocol, we just have to change the end hosts. Okay, so implicit just means that the only mechanism that we have to detect packet loss is these timeouts or duplicate acts. And here, changing a protocol only involves modifying the end hosts. And changing the end hosts is difficult, but it's not that hard. So TCP, for instance, has been changed numerous times over its lifetime. And the reason this is possible is because software is easy to update. Microsoft can roll out patches, and everyone will update their computers and so on. So changing hardware like switches and routers is very difficult, but changing software isn't that hard. Let's go move on to talk now a little bit about what's the ideal transport layer. All right. So what is an ideal transport protocol? The answer to this depends on the network. All right, so as an example, let's suppose that our network is, we have a person on Earth, and they want to communicate with a rover on the moon. All right, it's supposed to be a little rover that runs around and collects samples and so on. All right, so they have some radio waves that they transmit to the moon, and then this rover can send things back to NASA or someone on Earth. All right, so is TCP a good transport protocol in this setting? No, it's not. And the reason why is because the round trip time between the Earth and the moon is at least 2.5 seconds. All right, so in order to ramp up our TCP window, we'd send one packet and then wait 2.5 seconds to hear a reply, then send two, and so on. And so that's really not practical in this case, right? And in fact, with this large of a round trip time, if we assume that we have a 100 megabit per second link, and we have this round trip time of 2.5 seconds, then that means we can send 100 megabits times the round trip time, so 2.5 seconds. So this works out to be 256 megabits. So that should be capital, which is about 32 megabytes. So if we were to just send at our full rate here on Earth, we could send 32 megabytes before we received an acknowledgement for any data. All right, so this is before. All right. So a much better transport protocol would be one that takes advantage of this fact, that knows that you can send a lot of data before receiving an acknowledgement. And also, probably in this case, we know what the capabilities of this little rover are, and we probably on Earth would have some dedicated resources to communicate with this rover. So we might just want a protocol that sends at its full rate as fast as it can. And that would probably work much better than TCP in this setting. So another example where TCP doesn't work that well is in data centers. So I've talked a little bit about this, but let me give you a little more intuition into this. A data center network is almost the complete opposite case of an interspace protocol. So here we have very high bandwidth. And we have very, very low latency. All right. And because we have this very high bandwidth and low latency, as we saw, it's really hard for TCP to fully utilize a high bandwidth link like a 10 gigabit per second link. All right. So we need to do something different. All right. So here, some people at Microsoft have actually proposed, and they do actually use this in their own data centers, they propose using TCP plus explicit congestion notification. All right, now I just got through saying, well, explicit congestion notification requires every single network device to support it. So how can you possibly do this? Well, this is possible because there's only a single owner of a data center. All right, so there's a single owner of data center. And so because of this, they can buy whatever switches they want, and they can buy switches that support, let me just abbreviate this as ECN. So these guys just buy switches that support ECN. All right, and so now, in order to combine TCP with this explicit congestion notifications, now we have 3 congestion signals. So we have the standard one, we have TCP, we have the timeout, we have the triple duplicate ACK, and now we have this explicit congestion notification. So these are handled the same way as these are handled by TCP. All right. But this explicit congestion notification means that, well, there's starting to become congestion in the network. So here, instead of doing this multiplicative decrease that TCP does, we do an additive decrease in window size. All right, and because we have this ECN, we can keep the buffers very small. Or sorry, we can keep the buffers very low. We can keep them at a very low level. And so if you recall the incast problem I just talked about, since the average buffer size is very small, then the incast is not a problem because we can handle this sudden burst of traffic. So one more scenario where TCP doesn't do that well is when we have wireless networks. All right, so wireless networks have very high loss rates. All right, and as we know, TCP assumes that any sort of loss is its fault. So the way to overcome this problem is to use the lower layers to help TCP. All right, so we use the link layer Okay, so last week we talked about these different layers, and we have the application layer, then we have the transport layer, then we have the network, and then we have the link layer. So the link layer is responsible for communication across a single link. So in this case, we have an access point, or something like that, that's communicating wirelessly with another network card. Here, let's say it's in your PC, it's in your laptop. All right, so there'll be quite a bit of losses here, but this protocol that's responsible for this communication can actually be modified to detect the losses quickly and retransmit if it happens. All right, so the links themselves help TCP by quickly retransmitting lost segments. Okay, and now you'll go into much more detail about this later. Later in the course, we'll cover Wi-Fi networks, we'll cover the link layer, and so on. But I want you to get the idea that things that you do lower down in the stack can make a difference in the upper layers of the stack. All right. So if this link supports this sort of fast retransmit, if it handles its own error rate very well, then it simplifies the design of the transport layer. All right. So now, basically, this entire lecture, I have been hammering on TCP, saying it's not very good, and so on. But it turns out TCP, in general, does work really well. So TCP works very well on a wide range of networks. Okay. And in particular, it works really well on the networks that it was designed for, which are wide area networks. And this is what the internet is. Okay. It works very well on these wide area networks, works well on a wide range of round trip times. Now, the examples I gave you were sort of corner cases where we're communicating with the moon. Obviously, on Earth, you're never going to have a round trip time that's that large, right? So that's sort of a corner case, and it's like TCP wasn't designed for that. So it's no surprise it doesn't perform that well on it. Also, data center networks are pretty recent, and TCP wasn't originally designed for them. So it's also not that surprising that it doesn't work that well in them, right? But in general, it works really well for a wide range of networks. It's widely tested, so we know what the issues are, and we know workarounds for them. And finally, why do we use TCP? We use it because it's the best we have. All right. In the 30 years or so since its invention, no one's been able to come up with anything better, and that's why it's still widely used today. If your initial threshold is too high, then TCP will cause a bunch of congestion right away. When you start up a flow, it'll cause quite a bit of congestion in the network, right? Because it's exponentially doubling its window size, so on. And if it's too low, then it'll take you a very long time to find out how much bandwidth the network actually has. All right. So it means that in order to sort of optimize TCP's performance, we need a good threshold size.